All right, this meeting is now being recorded. So I'm going to go ahead and jump back into stats, and I'll keep watching the chat for people who might be coming in a couple minutes late. All right. So we've gone over a couple of basic metrics for describing data points, and then logful change as a way to compare groups, PCA as a way to look at multiple variables between groups, and then obviously we have figured out so Mel wants to do a comparison between these two clusters, thinks that this difference may be due to a gene that's turned on in Setosa but off in the other two species, and so Mel now has a hypothesis. So we are familiar with a hypothesis as a sort of educated guess. That's one way to think of it, based on some data that you have. But importantly, a hypothesis needs to be testable in some way, otherwise it is not super meaningful. So as an example, all sheep are white. If you see a lot of white sheep, that supports the hypothesis, but only one purple sheep is enough to disprove it. So the point here is that it's easy sometimes to find a lot of data to support a hypothesis. And so what we're after is it's easier to disprove a hypothesis than to say that you have enough data to support it, because you never know if you just haven't seen the purple sheep yet. So that brings us to the concept of the null hypothesis, which we also sometimes refer to as H naught. So the null hypothesis can also be thought of as the current or existing explanation for some phenomenon. In science, sometimes we phrase the null hypothesis as the pattern that we observe, which we think might be interesting, exciting, or explained by something cool, is just coincidence. So that's our null hypothesis. And because it's easier to disprove a hypothesis than to find enough supporting evidence for a hypothesis that we're happy about accepting it, we have our hypothesis, we have an accompanying null hypothesis, and we try to disprove that null hypothesis. Now, unlike the purple sheep example, in science, it is usually impossible to conclusively disprove the null hypothesis. So we would like to be able to be confident enough to reject the null hypothesis. So in order to accept our hypothesis, we want to reject the null hypothesis. But if we can't conclusively or decisively disprove the null hypothesis, how do we get to the point where we can reject it? So we have a few steps here. Design and perform experiments to get data that supports our hypothesis, and then perform statistical analysis on the data we've collected to see whether our results occurred by chance. If we can demonstrate that our results likely did not occur by chance, we can then reject the null hypothesis. So the null hypothesis would be our results were coincidental or occurred by chance. So going back to Mel's hypothesis about the iris species, the hypothesis would be something like, I hypothesize that the differences I observed between Setosa and versicolor and virginica are due to a gene that is turned on in Setosa but off in the other species. So what would the null hypothesis be here? I'm sure you guys all know this already. But as I said, in general, I designed this lecture to be at the level appropriate for students with no statistics experience or exposure, which includes often not having thought through what the relationship between a hypothesis and a null hypothesis. So an example null hypothesis here would be just the opposite of this phrase. Many null hypotheses can just be the opposite of the hypothesis that you're trying to test. So the differences observed are not attributable to a gene turned on in Setosa, but often the other species. So a good experiment that Mel could perform to test this hypothesis would be extracting RNA from several replicates of our iris species and perform RNA sequencing to see if there is a gene that is differentially expressed between Setosa and the other two species of iris. So that brings me to statistical hypothesis testing and the concept of a p-value or a probability value, which is very useful to us in these situations because it is the probability that the null hypothesis you're testing is true given the data from the experiment. So basically, the lower the p-value, the less likely the null hypothesis is to be true, because and so you want a low p-value, as low as possible, before rejecting the null hypothesis. Generally, in science, a p-value of less than 0.05 is accepted because it indicates there's only 5% chance that the null hypothesis is true. So you can go ahead and accept your alternate hypothesis. Another way of saying this is that a p-value less than 0.05 indicates statistical significance. So the outcome of the experiment likely not due to random chance. So I then ask, given what we've just learned, is it ever possible to definitively prove a hypothesis using hypothesis testing? Absolutely not. The best we can do is assign a probability to the null hypothesis being true and then make a decision about whether or not we're going to reject it. But very important to note, given that we're never able to, measure everything in the entire world, we're always sampling. The best we can do is assign a probability. We cannot definitively prove a hypothesis. So let's talk about adjusted p-value, which is a situation where we have multiple hypotheses that we're testing all at once in one experiment. So let's say Mel performed RNA sequencing on the irises. Well, some iris genomes, unlike human or mouse genomes, have over 100,000 genes. Each gene is a variable, which means that RNA sequencing would give 100,000 variables to compare between the iris species. So in this case, each of the genes or variables is treated as an individual hypothesis. So we're saying for this gene, our hypothesis is the gene is significantly differentially expressed. The null hypothesis is this gene is not significantly differentially expressed between these two groups. So what that means is we would be testing 100,000 hypotheses in this situation, or in this situation with our space flight and ground control data set, we'd be testing 21,000 hypotheses. So for data sets like this, where we have thousands of variables and we're interrogating each variable as its own hypothesis, it's important to mathematically adjust our p-values for what's called multiple comparison testing to avoid false positives. So what do I mean by that? Multiple comparison testing is comparing multiple variables between conditions. And why is this important? Well, let's do a thought experiment. Let's say Mel looked at the difference in expression of a random set of 20 genes. Well, just by chance, due to biological stochasticity, we would expect that on average, 1 out of 20 genes would just appear significant using the 0.05 or 5% p-value cutoff. So 5% of our data would appear significant using the 5% p-value cutoff. And that's just by chance. So that's what we call a false positive. This is a result that appears significant because we've just sampled enough, but in reality, this is due to random chance. So we can adjust the p-values to take into account the probability of false positives given the number of variables. So as the number of variables goes up, the probability of false positives increases, right? So if we have 20 variables, our probability of getting a false positive is 1 out of 20. If we have 40, continues going up from there. And so we can perform a mathematical adjustment to take into account the probability of false positives. Thankfully, we don't need to do this adjustment ourselves. Many bioinformatics statistical tools are going to generate, for each variable, a p-value, not taking false positives into account, and an adjusted p-value, which looks at the entire data set, how many variables do you have, and does a mathematical adjustment for that p-value to take into account the probability that your result is a false positive. So to kind of bring this into the realm we're talking about in gene expression data, we're going to run DESeq2. And so DESeq2 is set up to perform a hypothesis test between the groups that you give it on for each gene, asking the question, is this gene statistically differentially expressed, trying to disprove that null hypothesis. So for each gene, we get a p-value and an adjusted p. So I then go through a few questions here. What should be used when determining the significance of an experiment where 100,000 genes are considered? Should we use p-value or adjusted p-value? And clearly, from the previous discussion, we always want to use an adjusted p-value. But then kind of going back, when is it appropriate to use p-value rather than adjusted p-value? Because there might be some cases where using adjusted p-value is overkill. Maybe you don't have enough variables to justify that. So given a p-value cutoff of 0.05 or 1 out of 20, you would want to make sure that if you had an experiment with far fewer variables than 20 and you're using a p-value cutoff of 0.05, then you can go ahead and use the p. All right, so, and then this is something I haven't said explicitly yet, but after doing, yeah, exactly, Joel, yeah, raw p-value, yeah. So after making this adjustment, what the adjustment does is it makes it more difficult to be significant. So the raw p-value might have a bunch of false positives, so a bunch of values that are less than 0.05, but after adjusting for multiple testing correction, those values, a lot of them will be greater than 0.05, so which will generate more significantly differentially expressed genes, the p-value. It's a less stringent metric. So if we were to just go by p-value, there are more genes that pass the significance cutoff of less than 0.05. With adjusted p-value, we get fewer genes. All right. Are there any questions about what I've gone over so far? I'm assuming that this is not, this is something that is familiar to most or all of you already. But if not, let me know. All right. Great. Okay. So then I go through, we've just talked about sort of in philosophically, what is a p-value, what is an adjusted p-value, but how do we actually calculate that? Again, we're not calculating any of this by hand, but it is good to know what's going on behind the curtain. So in order to calculate a p-value, we can use a statistical hypothesis testing method such as a t-test. And a t-test is a simple hypothesis testing method, and so we're going to use this as an example. DSeq2 uses a more complex hypothesis testing method, but we'll use t-test to kind of understand what's going on there. The t-test compares the means of all measured variables between two groups. So for example, here I'm showing some kind of fake example data where we have a hypothetical gene X. We can look at the expression of gene X, the distribution in Setosa, and the expression of that same gene in Virginica. We can see the means of both of these distributions are kind of far apart from each other. There's a difference here. So the way to calculate, the way to perform a t-test, which generates what's called a t-score, is to calculate the difference in the group means, so mean 1 minus mean 2, divided by the variability of those groups, which is another way of saying standard deviation. So yeah, standard deviation comes in handy again. So we have the means, difference in the means over the difference in the standard deviation. Another way of saying this is signal versus noise. So most of the signal from each group comes in the middle of that group, and then there could be some noise and variability out at the edges. And so in order to compare the two groups, you have to take both of those into account. So after calculating the t-score, we get the t-score, and the greater, for a t-test anyway, the greater the t-score t-value, the more difference there is within that variable between the two groups. And we also get a p-value associated with each t-value, which describes the likelihood of the null hypothesis being true for that variable again. So here the null hypothesis would be there is no difference. There's no significant difference between these two genes. So another hypothesis testing method, and this is the one used by DSeq2, is called the Wald test. A little more complex than the t-test. The Wald test creates a mathematical model for which the null hypothesis creates a mathematical model for the null hypothesis, and then creates another mathematical model for the testing hypothesis, and then compares those two models to the experimental data and identifies which model best maximizes the likelihood of the data. So it kind of creates two imaginary mathematical models, like this is what it would look like if the null hypothesis were true. This is what it would look like if the alternate hypothesis were true, and then compares those models back to the actual data. Mathematical model here is a mathematical description of a situation. So specifying rules about how data should behave within that situation. So if the null hypothesis were true, this is what the data would look like. And to articulate this another way, the Wald test identifies a mathematical model for which the data that we have is the most likely result. Again, the Wald test returns what is called a Wald statistic, similar to a t-score, and a p-value associated with each Wald statistic. So that Wald statistic then is similar to a t-score. It's a value that describes whether we should reject the null hypothesis for that variable, accompanied with a p-value. And this Wald statistic is useful for ranking genes for downstream applications. So we have p-value, but we also have the Wald statistic, which is a description of the difference between the two groups. And for example, just as a note, gene set enrichment analysis is one downstream application. It's also abbreviated GSEA, and it identifies gene sets that involve a ranked gene list. Sum-based test. I'm not sure if it is a rank sum-based test. Yeah, rank sum is, I think, something different. I was just looking this up the other day. Other people who are familiar with this, please. Yeah. Yeah, so the man, right, so the man Whitney, that's a test. I'm under the impression, yeah. So I'm under the impression that the wall test does something slightly different. Um, let me just between.
Hey Lauren, it looks like the wall statistic is looking at a weighted distance.
Right. Does that, I think that's not, yeah, okay. I've just done some extremely cursory Googling. So my understanding, so a rank sum test is like where you have two lists of values, you rank them in their order, and then you compare where which gene, like the same gene is going to be in both lists, where did it fall in that rank, right? That's one way of doing statistical hypothesis testing. I believe that the Wald test does not employ that method, but I can take a closer look at this over lunch and give you a definitive answer. As you said, I think Armin, was that you speaking? You said that the Wald test has to do with weighted distance, and
Yeah, I didn't do much reading beyond that, but that's what I got in the first couple sentences of the wiki page I was reading. Um,
yeah, and
but
yeah.
the rank sum, like you're saying, seems like it's different.
Yeah, I think that the like I think of the wall test as like a fancy t-test. So and the t-test is I think also not a rank sum, I believe. Um, but I think of the wall test as like comparing distributions between groups rather than ranking them and then comparing. So I will look into this a little bit more. No, it's not from Susie. Were you talking about a t-test not being a rank sum test, Susie, or a Wald test? Thank you. Rank sum, yeah, yeah, that's what I thought. But we can use the statistic that comes out from the Wald test to rank genes for downstream applications. So just based on how different the genes were between the groups, sometimes there are downstream analyses like gene set enrichment analysis or ingenuity pathway analysis, which will identify gene sets based on a ranked gene list. So after we do the comparison, we get out a Wald statistic. We can then sort the genes based on that statistic. And the assumption here is that genes that behave similarly, like maybe belong to the same gene set, will get sorted into a similar area in that ranked list late after running the Wald test. And then that can be used as input to a GSEA or IPA. All right. So I now have just a few questions to illustrate the kind of bring home the idea that after you run a hypothesis test, you are expecting a statistical value, so like a t value or a Wald statistic, and a p value for each gene. Because each gene is a variable, we're testing a hypothesis. Each gene is a different hypothesis that we're testing. And then again, if we were to use a Wald test, we would expect, we would expect 100,000 Wald statistics and p-values. That's all I wanted to go over here. All right. So after we've talked about the way that we can test a hypothesis gene by gene, um, we've noted multiple times previously that we're not going to be able to do this comparison accurately before normalizing our expression data for differences in read depth. So gene expression data have different read depths per sample because a read depth is the total number of reads coming off the sequencer for each sample. And that number of reads for each sequencing run is split up between the number of samples. So depending on the total number of samples in each run, the read depth for each sample can differ. And so we have an example here where sample 1 just happens to have twice as many reads as sample 2. And we already saw in our spaceflight ground control data set, some of our samples have very different sequencing depth than others. So we have this situation in our data. So if we were to compare sample 1 versus sample 2 without normalizing, it would look to us like all the genes are more highly expressed in sample 1, but that's a technical artifact, not a biological signal. So we first have to normalize based on read depth to allow direct comparison of gene expression between samples. So this brings us to the first step of DSeq 2, which is normalizing using the median of ratios method. So there are multiple steps to the median of ratios method. I'm going to go through all of them, and please stop me if anything is unclear. So the first step is, let's say we have our little tiny little toy gene expression data set here. We're just looking at 2 genes. Each row is a gene. Note, for example, these genes have gene names rather than ensemble IDs, because this is the example from DSeq 2. And then we have 2 samples, sample 1 and sample 2. And we have values, our initial raw unnormalized values for each gene for each sample. So the first step here is to create what they call a pseudo-reference sample. And this pseudo-reference sample is equal to the geometric mean for each gene across all samples. So the geometric mean is a little different from regular mean. It's just the square root of the product of all the data points. So in this case, simple, take the square root of these 2 values. And so we now have a new column in our data set called the pseudo-reference sample, which has the geometric mean across all genes. So we're going to use this. This is kind of like a summary of each gene across all samples. We're going to use this in a minute. The next thing that we do is for each gene in a sample, the ratio between that sample and the pseudo-reference is calculated. And this is done for each sample. So we add a new column for each sample, which is just the ratio of that sample over the pseudo reference for that gene. So the assumption here is we are understanding, again, we're understanding how different each sample is from the mean. So since the majority of genes are not differentially expressed, the majority of genes just in general in biology are not going to be differentially expressed. So the majority of genes in each sample should have similar ratios within the sample. So you can even see that here, where the majority of the genes, so the top 4 genes here, we're now looking at more than 2 to kind of get a bigger picture. So the top 4 genes under sample 2, after taking the ratio, all the ratios are pretty similar. They're around 0.7. But then MLV10 is a little different. So it's 1.35. All right, so put a pin in that, go on to the next step. So we then the ratio helps us understand the distribution of a different expression across each sample. So we have a range, right? We have 0.7 to 1.35 in sample 2, and we have right around 1.3 all the way down to 0.5 in the little example we have for sample 1. So what we do now is we take the median value of all of those ratios for each given sample, and that median value is taken as the normalization factor or the size factor for that sample. So what we're trying to get at here is we know that each sample might have different sequencing depth, but they all should have, between samples, there should be a similar range. Like we know that some genes are going to be differentially expressed, but the range for each sample should be similar because this is all from the same biological experiment. So we've gotten our range of ratios for each sample, and we've now calculated our normalization factor, which is the median value. This is the value we're going to use in the next step to adjust each sample for read depth. Okay, I think there was one more thing I wanted to highlight on this slide. So yeah, so this method is making the assumption that most genes are not going to be differentially expressed. And so this method is going to be robust to sort of imbalance in, let's say, up and down regulation or differentially expressed genes, because, as I said, we're calculating kind of the range across an entire sample. Okay, so now that we have our median value of all those ratios for each sample, we use that as the size vector for that sample. And we then divide each raw count value in each sample by that sample's normalization factor, and that gives us our normalized count values. So at the end of the day, we have a new matrix with these normalized counts. How does that scale across more than one sample? Or is this only applied for pairwise comparisons? No, you can do it across lots of samples. So here I'm just showing 2 samples, but you can do this on a data set with hundreds of samples. So this is done on a sample by sample basis. So it doesn't matter how many samples you have, it just happens. All the calculations, the first calculation is performed across the entire data set to get your pseudo reference sample, to understand the distribution of each gene across the whole data set, to kind of understand the ups and downs based on sequencing depth, and then everything else is calculated within each sample. Does that answer your question? All right. Does anybody else have any questions about median of ratios? Okay, great. All right. So I then just have a couple of thought questions here. If we didn't do normalization, we would expect to get, if we get differentially expressed genes in a comparison between 2 samples, where sample 2 has 4 times the read depth as sample 1, we would think, oh, all these genes are differentially expressed, and they're all higher in sample 2. And this is not representative of biology, which is why it would be problematic. So it would be impossible to tell where overexpression was due to true biology and where it's due to sequencing depth difference. Just kind of hammering this point home. All right. So I think I've kind of hit all of these points before, but this slide is to summarize how we're going to perform differential expression analysis in DESeq2. So after normalization, we then run DESeq2. This is, again, 100,000 or however many genes you have. Hypothesis tests run at once. DESeq2 uses the Wald test for differential expression analysis hypothesis testing. And then the null hypothesis we're testing for each gene is this gene does not change expression significantly between the tested groups. All right, so that's, so DESeq, before we actually get to the Wald test, there's a second step. First step was median of ratios normalization. Second step is estimating gene-wise variance, which is also called dispersion in DESeq2, but the terms are interchangeable in this context. Before we run the Wald test, we need to estimate the gene-wise variance or dispersion. So we already talked about how we need to filter out genes that have very, very low expression. We did a cutoff. There's still plenty of genes with low expression, and these genes, they may be just biologically lowly expressed, but what that means is that the chances of them being missed in one or more samples is higher, just because they're not expressed that high. So they might have, a real count value, a biologically real count value in some samples, and then just be missed in other samples. So the result of this is that the variance or dispersion estimates are unreliable for these genes. So it might look like these genes kind of have really high variance because they're expressed in some samples, but not other samples. But we just know, due to the nature of RNA expression and RNA sequencing, that genes with low mean counts tend to have artificially inflated variance. So this is solved in DESeq2 by estimating variance or dispersion by sharing information across genes. So the assumption here is that genes tend to have similar variance, similar dispersion, so you can borrow information from genes that tend to have similar variance in some samples and assume that they're going to continue having that type of variance in other samples. So DESeq2 kind of estimates and fills in the variance or dispersion by sharing information across genes, across the entire data set. Yes, so this is what I just said. With this approach, DESeq2 assumes that genes with similar expression levels also have similar dispersion or variance. And the dispersion for each gene is estimated using a mathematical method called maximum likelihood estimation that Amanda talked about. And so this just means that the most likely estimate of dispersion is calculated for each gene, given those gene expression values from all of the replicates in each group. So this is important because variance and dispersion play a large role in the actual Wald test, a mathematical model. So it's important to have accurate estimates for variance across the entire data set. All right, so finally, I kind of made a big deal about how the Wald test generates a mathematical model for the null hypothesis, like this is what the data should look like if the null hypothesis is true, and similarly generated a mathematical model for the alternate hypothesis. This is what it would look like if the alternate hypothesis were true, and then compares both those models to what the actual data look like. Now, the Wald test has to use a baseline mathematical model to generate its specific models for the comparisons. So the type of model that the Wald test uses is dependent on the shape or the distribution of the data. So while each data set is slightly different, RNA sequencing data tends to have the same shape overall. So here again, a model is a distribution shape and then the numbers that specify that shape. So the distribution shape, that's kind of general, that's reusable every time, and the wall test has to be told which general type of distribution to use, which will be the most accurate for the type of data we're using. But then the numbers that specify that shape, mean and variance, that's what's specific to our data set. So RNA sequencing data, as I mentioned, has a specific shape. The majority of the genes have expression value close to 0. That's just biology. Most genes are not expressed at super, super high levels, but many of them are. And in fact, there's an extremely long right tail because there's no upper limit for maximum expression value. So we're just measuring counts in the cell. Sometimes some genes are expressed at very high values. So specific shape for RNA sequencing data. Now, count data, just in general, is sometimes modeled using the binomial distribution. So the binomial distribution, also the coin toss distribution, and when I say count data, I don't just mean RNA-seq data, I mean just like any type of count data. The binomial distribution shown here is basically illustrated by the probability of getting heads when you toss a coin a certain number of times. So like in this graph, if you toss a coin 40 times, probability of getting heads is about half the time. However, the thing is, this works really well when you only have a few number of data points, but does not work very well for RNA sequencing data, where there are lots of data points. So instead of the binomial distribution, here we use the negative binomial distribution. This is most appropriate for RNA sequencing data. And note that this plot looks really similar to what we were just looking at with RNA sequencing data. So it makes sense that we would use this distribution, just kind of visually speaking. So DSeq2 uses the negative binomial distribution to create models in the wall test for differential gene expression analysis. And so this is one of the strengths of DSeq2, that they use a distribution that is accurate and appropriate for RNA sequencing data, and not all statistical tools do. That's why I showed the binomial distribution, because it's sometimes used to model counts data, but there are assumptions within that distribution that don't hold for RNA sequencing data. So just wanted to point this out as one of the strengths of DSeq2. All right, so this brings me to the end of the part of the lecture I wanted to go over before we get back into the notebook. Are there any questions before we get back to the notebook? All right, so I'll just end by saying that I look forward to talking to you a little bit more in the debrief about this lecture, things that I could, improve or do better, things, you all know your students really well, so ways to explain these concepts that would make sense to your students. So I look forward to hearing from a bunch of experienced educators on how I can improve this. All right. So let's get back to implementing some of these concepts. All right, so is everybody still logged in to SMCE? And I'm noticing here that, for example, I don't have a kernel running. So my kernel has died. So I don't know why exactly, but I'm going to go ahead and restart it here by clicking on the no kernel idle and selecting the proper kernel, which is the RCon environment, GL4U R. Initializing, connecting, and then it should say idle. So does anyone not see the con environment I'm showing here and idle? All right, great. Did anyone else have to restart their kernel? Recall that when you restart your kernel, you have to run through everything that you've done before. But hopefully I'm the only one who has to do this. Okay, great. Thanks, Akami. Assuming that no one else is having errors, we can go ahead and move on to what we were just talking about, data normalization. And please let me know in the chat if you have any issues with SMC Jupyter Hub. All right, so recall, right, our current counts matrix, which is held in this variable raw counts, and we also inserted this into the count slot in our DSeq dataset object, needs to be normalized for sequencing depth. But before we do that, I would like us to take a look at let's investigate the data structure. All we've done so far is we've looked at the matrix, which let us see, the first few rows, but let's use PCA, as we saw in the stats lecture, to investigate the overall structure in the data. So we're going to take a step back from the DSeq dataset object and just work with the raw counts data frame, which holds our counts data. So the first thing that we're going to do is we're going to do a log2 transformation, because that makes it easier to calculate the principal components. So remember, the log2 function in R can calculate the log of a data frame. Why am I adding +1 to this data frame before calculating the binary log? Any ideas? Exactly, zeros. So this is what's called a pseudo count, and it is an accepted practice in statistics and bioinformatics to add 1 to your data frame, just so that all of your zeros become ones, and you also add the same number to each value. All right, so I'm taking the log and assigning the outputs to a new variable called exp_raw. And then I'm calculating principal components using this handy function called prcomp. Which calculates the principal components for an expression data set. Note that I have to first transpose this data set using another handy function, little t. So this will transpose the data set so that instead of genes on the side, we have genes on the top. And I'm assigning the outputs back to a variable called PC_raw. So let's run this pre-populated cell and then take a look at the PCs using summary. So I'm going to let you guys run the summary cell and answer the following questions. So are these in Mentimeter?
We should all be seeing the right question now.
And can we share the link again for
Yeah.
those who might have lost it? Thanks. All right, so how many PCs were detected? Let me know. I'm going to go ahead and stop now, Armin. Thank you.
Yep.
So, quick preview. Everyone said 12. Very good. So I will go ahead and run summary here on my screen. And we get a nice little summary of our PCA underscore raw variable that held our PCA results. So as you can see, yep, 12 PCs detected. Great. Okay. So how about this next question? What percent of the variance is explained by PC1 and what percent of the variance is explained by PC2? But now, so little preview here, lots of very similar answers. So absolutely, you guys are all right. And for those of you who didn't get a chance to answer, please shout out if this isn't making sense. But the hint says see proportionate variance. So this is the row in this little data frame matrix that helps us understand the proportion of variance assigned to each principal component, which is another way of saying how much variance is explained by each principal component. So, yep, 18% approximately explained by PC1 and 13 approximately percent explained by PC2. All right, so we have PCs in order of 1 through 12. How are they being ranked? What determined this order? Thank you so much. I'm going to stop it now. Okay, so yes, by their names, very nice. Ranked in order of greatest to least proportionate variance, but standard deviation by proportion, highest lowest variance, standard deviation decreases proportion variance by proportion variance. Yeah, so you're all right. There's a little more to it than this. So let's take a look here. So starting with the top row, as some of you noticed, standard deviation decreases as we go along the principal components. Proportion of variance also decreases, and cumulative proportion increases. So the point is that all of these metrics are related. And then, of course, obviously, they're ranked by their names, PC1 through PC12. Thank you to whoever said that. Okay. So we've calculated our PCs. We've just looked at the summary. We haven't actually done anything with the PCs themselves. So let's go ahead and create a plot of the first two PCs in a scatter plot, so like we were looking at in the lecture. The first two PCs do explain the majority of the variance in the data set, right? So 18%, 13%. The next one down is 9%. So we're going to use a visualization function in R called autoplot, which is able to automatically take the first two columns in the data set that we give it, PC underscore raw. We also need to pass in an argument called data, which where we give it the sample table so that it knows which samples belong to which groups, so it can color the plot by groups, which makes it nice to look at. We specify we want to color the plot based on condition, which is the name of the column in the sample table. So this function is set up so that the color argument is expecting the name of a column in the whatever is passed in for the data argument. In this plot, we're going to label all the samples with their names. We can pass in the specific label size and point size, and then the alpha. Does anybody know what alpha is? So alpha exactly stands for opacity. It's a range from 0 to 1. So an alpha of 1 means that all these points are completely opaque. an alpha of 0 would mean they're all invisible because they're all see-through. And so an alpha of 0.5 would be like halfway see-through, which is nice. We have a lot of points and they overlap. And then this little thing that we add at the end has to do with formatting the plot itself. So the background is white and the size of the plot. All right, so let's go ahead and run this cell, and we get a nice PCA plot here with PC1 on the x-axis and PC2 on the y-axis. Our points are colored by condition, and we have the name of each sample imprinted on each point. So before we get into answering some questions about this plot, let's save it. So we're going to save this into your home directory here. PCA dir is that PCA directory that we set up at the very beginning. We're going to write out this plot with a descriptive name, GLDS104, PCA raw. So we haven't normalized, this isn't using the normalized data yet, with labels and some width, height, DPI. Note we're using file path to stitch together the path to the PCA directory and the name where we want to save this plot. And then ggSave is a handy function from the ggplot2 library for saving plots. So let's go ahead and run that next cell. So that shouldn't have any output because it's just saving the plot. All right, and then let's do all of this one more time, except here we're going to set label equals to false instead of true, so that we get a nice plot without the sample labels. Because as you can see, the sample labels kind of overlap each other. They're a little bit hard to read. They are nice to have in some situations, but it's good to have both versions of the plot with and without the labels. All right. So going forward, we're only going to make plots without labels, just FYI. But you can always change the label back to true if you're interested. All right, and before we move on, let's go ahead and write out the principal component values of the raw count. So that's PCA raw. We're using the $sign operator. Remember, that's a way of accessing a specific part of a data structure in R. We just know that the X slot of the PCA results is the one holding the values for the PCs. We're going to write all of that out again to our PCA directory and into a CSV file. Let's run that cell. And then let's take a look at these PCA plots and answer some questions. So taking a look at this plot, do you see a pattern in how these samples are separated? Let's take a look at the answers. Okay, so based on PC1, GC and flight are separated by PC1. Yes, separating based on condition, mostly on PC1. Flight spread across Q103 and GC is in Q2. Yep. GC are clustering. Flight very dispersed. Good observation. Yes. Not sure. We'll go over it. Okay. Flight and GC, different clusters. Flight samples are more spread out than GC. Yeah. Okay. So what I was getting at here, and you guys have gotten ahead of me a little bit, which is great. So what I was getting at was, yes, a separation along PC1 appears to be separating out the flight and ground control conditions. And then some of you also noted that the flight samples seem to be way more dispersed along PC2, interestingly, than the ground control samples. All right, and then really quickly on Mentimeter, would you expect the data points to separate like this based on their biological conditions? Why or why not? Actually, you know what, let's not do Mentimeter for this because you guys really already got at this in this first question. Since we do have two biological conditions, as you pointed out, the sample separating based on these conditions makes sense. So if I had run this experiment, I would be pretty pleased that even before normalization, the raw data are already separating out on the biological conditions that I set up. So there's a clear difference in flight and ground control, and that difference appears to account for at least 18% of the variance in the data. All right, and I believe that brings us to lunchtime. Yes, they're separating on condition as long as it isn't a batch effect. Yeah, that's a really good point. There are times when it is impossible to separate out potential batch effect from biological condition because you have to send your flight samples to space in a batch and you have to keep your ground control samples on the ground in a batch. So there are, as I'm sure everyone knows, ways around this, but yeah, from this point, we're able to look at what contributes to PC1 to get some big picture biological significance. So when we do differential gene expression analysis, we'll compare flight and ground control, which is basically making a comparison across PC1. We're going to get genes that are differentially expressed between the two groups, and that will help us understand big picture biological significance. Yeah, great question. All right, lunchtime. We will pick this up after lunch. Thanks for all the great questions. Please be back by 12 p.m. Pacific time.